Hello everyone, my name is Rudayna Subeh. I am a PhD student working as a research assistant at Yulish Research Center, and on behalf of my co-authors, Professor Antoine Tordu from Wuppertal University and Dr. Mohammed Mir'i from Arab American University, I am pleased to present our work entitled Quo vadis, Pedestrian Trajectory Prediction in Complex Architectures. It's important to understand the movement characteristics of pedestrians inside complex architectures. As you can see in this slide, we have various types of facilities with different complex geometries like train stations, airports, shopping malls, and so on. And also we have open environment and closed environments inside buildings. Investigating and understanding the pedestrians' walking characteristics in such facilities will help us in several applications, such as legal regulations in civil engineering, safe planning for events to avoid dangerous situations, and also in computer simulation tools. Some of these facilities, such as the one in the middle, contains a corner part that control the directions of pedestrian movement and influence the movement characteristics of the pedestrian. In our work, we are interested on quantitatively understanding and investigating the microscopic characteristics of pedestrians at 90-degree corners. So, why it's important to study the turning movement at corners. Pedestrians flow in such corners is restrained, especially in crowded situations and emergencies, due to the combination effects of the turning angle and the high desired speed. As we can see here in this figure, in the Who Concert crowd crush, the pedestrians are panic at the entrance corners, and they are trying to push each other, and they are trying to increase their desired speed to go out and save their lives. In such cases, the combined effect of pedestrians who are trying to turn with a high desired speed will lead to a blockade, resulting in dangerous situations. This is why it's important to focus on the fundamental research which investigating the turning movement to avoid such situations. Until now, it is still a challenging task using physics-based models to simulate and predict the pedestrian's turning movement within corners in crowded situations. Focusing on reviewing the literatures that investigate this type of movement, I mean the microscopic and macroscopic movement characteristics at corners, we can divide the research into two categories. The first category models the movement of pedestrians in different types of corners and different number of pedestrians who move inside these corners. For example, in her research, he conducted a comparative analysis of pedestrians' movement characteristics at different types of corners for different densities. And also, he proposed advanced social force model introducing the visual angle, walking preferences, and steering force parameters to model the microscopic movement characteristics of pedestrians. Another study for Dias, who studied the individual movement characteristics of pedestrians in different types of corners, and Schreiber, who modeled the wall pedestrian repulsive interactions at the entrance corners and developed a strategy to determine the next desired direction of movement. The second categories of research concentrate on performing experiments for different corner scenarios and also for factors analysis such as Yi, who conducted experiment in 90-degree corners, Akiyama, who conducted experiments in circle and different curves, and he measured the gate motion for pedestrians, and after that he conducted a comparative analysis. Also, Dias, who studied the movement characteristics of pedestrians in straight and other angled corners, and also Imai, who measured quantitatively the body, head, and eye movement in circle experiments, and he compared it for the movement, the body and head eye movement of pedestrians while walking inside a straight corridor. But it is still a challenging task to model the corner movement in crowded situation, and some questions still not answered yet, such as: can we predict the future trajectories of pedestrians for different densities, especially when we have a crowded situations like here, where the human and human interactions and the overtaking behavior between pedestrians become higher? Also, here in the second figure, which present the walking process of individual pedestrian walking around the corner. Some literature divided the walking process to 5 areas: walking straight, ready turning, turning, distance adjusting, and again walking straight. And some and other research, they divided only, like here, they divided it only for 3 stages: walking straight, and after that we have a turning angle, so we have a turning movement, and after that we come back to walking straight. The question here is how the walking process differ for different pedestrians densities, and what are the influential factors that will control this movement in different densities. So we need to answer these questions and to understand more the movement behavior in these type of situations. To address these challenges of physics-based models, we are planning to use neural networks. Why? Because using neural networks, we will be able to capture patterns from input data without modeling assumptions, and also we can estimate the multiple coefficients to solve complex problems that are hard to achieve using physics-based models. Many studies based on neural networks show promising results for predicting the future trajectories of pedestrians. Most of these studies inspired by Alahi research in 2016, who used the long short-term memory to predict the future trajectories of pedestrians. He introduced a pooling layer to model the interaction between pedestrians, between the subject pedestrians and other pedestrians around him, the neighbor pedestrians. And after that, he decoded this encoded behavior to predict the future trajectory of the pedestrians. But still, such approaches are developed to predict the future trajectories in low-density situations using specific type of datasets, whereas the algorithm relevant for high density is still open, and this is what we are trying to work on. So datasets for several experiments are available. For example, as we can see in this slide, we have experiments for 90-degree corners for different densities. We have datasets for pedestrians walking in straight corridors. We have datasets for pedestrians walking in oval corridors and crossing. And also we have many datasets for different scenarios of pedestrians movement. And we will use these datasets to develop our data-based algorithm to predict the future trajectories of pedestrians. So to focus the idea or to talk more deep on what we are working on right now, we are trying to develop a data-based algorithm to predict pedestrians' future trajectories, especially in corners and turning movement. And we will build this algorithm for different density levels of pedestrians. And we are trying also to understand and discover what are the influential factors that impact pedestrian turning movement in unidirectional flow. This study will help us in the future to build a more generalized algorithm to predict the future trajectories of pedestrians, maybe in different types of complex architectures. To summarize the presentation, in this presentation, I presented the motivation behind studying and investigating the movement of pedestrians inside corners and why it's important to study this type of movement. Then I presented the physics-based research that focus on turning movement and why it's still a challenging task to use physics-based models to model the walking process of pedestrians in highly crowded situations. Furthermore, I talked about the data-based algorithm, which used to predict the future trajectories of pedestrians using neural network, and what are the advantages of using this approach for pedestrian dynamic. For our current work and future work, we are developing a data-based algorithm to predict the future trajectories of pedestrians in corner corridors. And we will use the neural network to understand the influential factors of this type of movement. We are planning to evaluate the algorithm experimentally using empirical data. We will start with 90-degree corners, and after that, we want to apply it for a different type of experimental data sets for several densities, of course. And finally, we are planning to make a comparative analysis with other classical models. Thank you for your attention.